Hello everyone again, and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in here we're going to be exploring some interesting things involving quantum and a little bit of introduction that led to some interesting outcomes that we're seeing in terms of quantum coming from classical mechanics. And we know, of course, how classical mechanics actually began, and we all knew how they actually thought that, you know, what happens in the real world actually happens at a small level. But in this particular case here, we're going to be looking at, you know, how to determine the energy and the wavelength when a specific subatomic particle actually moves from one energy level to another. So before we actually jump into this particular question, please don't forget to hit that like, share and subscribe, by that way others can actually check out these videos, and also subscribing because, hey, subscribing is free. So let's dive into this by actually looking at this particular question and breaking it down, and how you'll be able to actually approach this question. There are multiple ways to go about it, but you know what, we're going to go into the basics of how this actually was originated. Now, we know that in this particular case, for the solution, we actually need to have some key concepts in mind, and these key concepts come from the question itself. It says, first, what is the quantity of the energy? So quantity of energy, we know that in this case here, it is represented as, you know, change in energy, or yes, we'll represent it as change in energy. And the change in energy here that is emitted when a hydrogen atom, keep that in mind, we're dealing with hydrogen atom. So when you say hydrogen atom, right, why specifically hydrogen atom? There are many things to take into consideration. One thing is that if you have many electrons, the energy could be different, and also how that is going to influence the shielding system is going to be actually contributing to the energy. So speaking of hydrogen atom, we know that hydrogen has what? Just a proton, which is represented as, you know, the center of the atom, and we have a couple of energy levels that are actually out there. One will be, you know, you could make this your n, of course, is going to be equal to 1, which is the ground state. And we have the next one, which is in this case n equals 2. Sorry for my disoriented energy levels. And our next one here we're going to deal with is n equals to 3. And you're asking, why 3? The reason why we're dealing with 3 as the maximum number of n value is because this question actually says that the electron of the hydrogen actually relaxes from n equals 3 to n equals 2. So we're dealing with these two energy levels right here, the first one here, and we're dealing with the other one right there. So what is happening here? We have electrons, we have just one electron, and that one electron is going to be moving from one energy level to another. And this actually comes into play when dealing with, hey, quantized states. And that was actually originated by a particular scientist called Planck. And Planck, of course, his full name is Max Planck. He actually introduced the concept of quanta, because back then, you know, before his time, there were concepts roaming around that, hey, we got some interesting things happening classically, and how about we apply those concepts concerning energies being continuous in smaller objects, smaller atomic particles. And what they realized was that, hey, looking at and observing the black body radiation, and also some interesting observations that weren't matching up with the data, they were like, well, what is going on? And then Planck was able to change his ideology about quantum, and also how to explain the experimental data based on new ideas concerning entropy, concerning the Boltzmann distribution, and so many more, enough for him to actually finally come up with a particular explanation for the reasons why the black body radiation actually happens, and why the ultraviolet catastrophe is not actually a thing, and also how entropy and the Boltzmann distribution of particles do make an impact in how the curve actually relating the intensity to the wavelength according to the spectrum actually works, and why you see that coal is actually visualized as dark when it is not heated, but then when you increase the temperature, it changes color from red to blue and all that fun stuff. So that led that idea to actually move on to the early 20th century, and then Ernst Rutherford actually introduced the concept that, hey, electrons are actually around the specific dense region, and in this case the dense region is just mainly protons present in there. And so in this particular case here, that idea was actually combined, those ideas were combined together by Bohr to introduce the hydrogen atom relative to the electrons, and how electrons are positioned based on energy levels that are actually quantized rather than being continuous. So in this case, you will need to have a specific energy to exist in n equals 2, and now for you to move up, you will need to gain a specific amount of energy in order for you to actually get to the third energy level. And in order to come back, it means that the other case where in this part, once that electron is in the third energy level, and then it actually in this case wants to go back to its actually original level, in this case n equals 2, what happens is that that electron that was here will actually lose that particular wavelength or energy, and so therefore it will actually drop back to the n equals 2. So that leads us to our specific question, where we're actually saying that the electron relaxes, which means it goes from a higher energy level to a lower energy level. So looking at this, actually Bohr actually came up with the idea that, hey, enough for you to determine that much energy, you need to actually know this relationship through the emission spectra, that the energy that is actually required is actually equal to the n, which is Planck constant multiplied by the speed of light, over the wavelength. And this wavelength here, that expression is actually equal to negative the Rydberg constant multiplied by the 1 over n initial all square to or minus the 1 over n squared of the final energy level. So therefore, since we have this expression taken care of, we are actually going to focus on this particular region right here first, because one, this negative sign tells us that, hey, there is an attraction between the positive, which is the proton, and the electron. But then when that is actually taken away completely from that particular atom, which is the electron, it means that it's going to be a positive sign, which means that you are at the zero energy system. So in here, we actually are going to be focusing on this particular expression because we have a constant, we have our n initial, and in here we know that our n initial is going to be equal to our what? 3, and our final energy level is going to be 2. And so once we have those givens, and we know that the specific RH, which is the Rydberg constant, which is equal to 2.18 times 10 to the negative 18 joules per electron, we'll be able to determine what the energy is, and hopefully from there we'll be able to determine what the specific wavelength is. So therefore, once you put all these numbers into this equation, what we're going to have is, for analysis, we are able to actually determine what the energy is. And the energy in this case will be, let's label this to be energy B, which is EB. That is what we want to find. And so therefore EB is equal to negative 2.18 times 10 to the negative 18. Don't forget your unit, joules per electron, because we're dealing with one electron. And this is going to be multiplied by everything in the bracket 1 over, we know that n initial is actually 3. So in this case, we have 3 squared minus 1 over, we have 2, which is our final energy level, all squared. And this here will be solving the bracket, negative 2.18 times 10 to the negative 18 is actually going to be multiplied by, in this case, 1 over 9 minus, in this case, 1 over 4. And so therefore, once you solve all this, you'll be able to actually come up with your energy, which is equal to, in this case, oh, don't forget your negative sign here. So it means that the negative sign is going to cancel the negative signs, and what we have here is a positive value of the energy. So therefore, our energy will be 3.028 times 10 to the negative 19 joules per electron. So that is how you're able to determine the energy that will be released when an electron goes from a higher energy level to a lower energy level. And then our next stop is, what is the wavelength? How to determine the wavelength of that specific light that is going to be released by the electron in order for it to go back to its lower energy level. So therefore, to determine this particular wavelength, we know that our speed of light is equal to 3.0 times 10 to the 8 meter per second. And since we have this, then it means that we are going to be using our specific equation, which is E equals to the Planck constant times your speed of light divided by your specific wavelength. And so to rearrange this, we are going to have our wavelength up and our energy down. So therefore, our wavelength is actually going to be equal to our Planck constant multiplied by our specific speed of light, or divided by our energy, AB. So therefore, moving up over here, we know that in this case, our wavelength, which is the wavelength that is going to be released, is equal to 6.62 times 10 to the negative 34 multiplied by our speed of light, 3.0, and let's make this times 10 to the 8, and this is going to be divided by our energy, which is 3.028 times 10 to the negative 19. Take note here that the specific, in this case here, the units must actually match up, and once the units they don't match up here, we're going to be able to determine our answer, which is going to be, in this case, equal to 6.558 times 10 to the negative 7 meters, or you can transform it to nanometers in this particular case right there. So if you want to make it to be nanometers, it will be 655.8 nanometers. So that is about it for how to actually determine the wavelength coming from the energy that we have right here, and also looking at how the energy is actually gotten from our specific Niels Bohr's hydrogen atom energy equation, which uses the Rydberg constant with relationship with this particular expression. And this expression, take note of this expression, because this expression helps us to notice that, hey, looking at the energy levels, we actually go in smaller gaps as you alternate from one energy level to another. So from n equals to 1 to n equals 2, the energy gap is much bigger than going from n equals to 2 to n equals 3, and so on, and the gap gets smaller as you alternate from one energy to another. Therefore, as you increase in the radius of the atom, you have a decrease in the energy gap as you go from alternating energy level to another. So that's about it for this particular video. Hope you're able to understand this. Please hit the comment down below, let me hear your thoughts, and please don't forget to subscribe. By that way, others can actually check out these videos, and also subscribing is free. And see you on the next one. Stay smart and believe in yourselves.